Good afternoon. We're here to talk about a simple serial monitor, possibly two, written in JAL. Over the past couple of sessions, we've discussed serial monitors. First of all, just how to use the serial monitor, and then how to use the serial monitor more efficiently. But both of those were in the context of Arduinos and Arduino Array. And so I thought it might be a good idea to have a wee look at how we do it in JAL. When I say I think it would be a good idea, actually that was kind of thrust upon me, as they say. A client member, who shall remain nameless, let's call him Charlie, you know Charlie, wanted to send debug messages to a serial port. And if you've got a modern PIC, one of the bigger PICs, then that's really not a problem. You can have both hardware or software serial libraries, and we could have done that in a very short time. Except this client wanted to run it on his PIC 12F675. Now the 12F675 has only got 8 pins. It's only got 1023 bytes of main memory, and he was writing in JAL. He wanted something that he could bolt onto an existing JAL application and use it. So that kind of put some restrictions on what we were being asked to do. So we had a chat, had a look, and this is what was planned. Charlie's application lives on a piece of perf board, on a piece of error board. That's everything to the left of the 12F675 there. I'm going to move my head down here out the road. He's going to supply 5 volts and 0 volts and a single output pin to a serial to PIC converter. Now the serial to PIC converters, if you haven't met them, they're there. Costs the princely sum of £2.99. On the left-hand side, you have a 6-pin serial port at TTL levels, either 5 volts or 3.3 volts. Just to the right of the 6-pin header, there's a little jumper, and that little jumper decides if it's 5 volts or 3.3 volts. Then we've got the FTDI chip. The standard chip for doing this is made by a Glasgow company called FTDI. And beyond that, there's a mini USB. Down either side, there are other pins for adding other things, although I very, very rarely use them. You couldn't buy an FTDI chip and a USB socket for £2.99, so there's really very little sense in considering making something like this for yourself. And while we're on eBay, there's what I'm going to develop the solution on. This little board costs about £5. At the top of the board, there's a black barrel jack. The board itself comes with, along with the board, you get a cable that's got a USB-A at one end and a barrel jack connector to fit that at the other end. So all you need to do is plug this into a spare USB port and you can develop your, or at least you can power your 12F675. Next to the barrel jack, there's a 6-pin ICSP socket. Now this 6-pin ICSP, in this case, is a JST connector, not the more usual pin header version. And because it's a JST connector, the connectors are just a wee bit finer than we're used to. And for that exact reason, I simply desoldered that and replaced it with a standard 6-pin header, like we just saw on the extreme left-hand side of that little thing. That 6-pin 90-degree pin header is what I now use on there instead of the JST. Next to the power jack also is a big white and blue switch. That's a power switch. That simply disconnects the power from your PC or your hub or whatever it is you're using. So when you press that button, everything's switched off. Then there's a pot, and the pot's connected to one of the pins on the PIC chip. Then there's a row of components that includes decoupling components. It includes a power LED, so you can see when this thing's powered. It includes a couple of user LEDs that are connected to the pins of the chip. And that's about that. Across the bottom, you see 3 buttons. One button's permanently wired to the reset, pin 4 of the chip. And the other 2 buttons, again, go to the pins on the chip. Now, all the things that go to the pins in the chip go to them via those 8 yellow jumpers. And the beauty of that is you can just pop those jumpers and you've suddenly just got the bare chip again. Or you can leave a switch if you want a switch, or if you've got something else you want to put in, you can put it in. So you can develop all sorts of componentry on this wee board. But as it is, with 2 uncommitted push buttons, 2 uncommitted LEDs, and an ADC input from a pot, you can do quite a lot with it, just as it stands, just as it comes out of the packet for China. And as the man that tried to get to Tralee, but was decided to ask a local, how do I get to Tralee? And the fella says, I wouldn't start from here. Similarly, I'm not going to start from that little board, that little development system. What I'm going to do is make the signal that I want to make, RS232, this on a bigger PIC or on a PC or some way that I know that I trust, that gives me a sensible RS232 output. I will then, as I've written here, go to school on it. I will measure the time and I will look at the phase. I will look at everything about it. And once I've done that, I'll then try and make that same signal on the little PIC. And once I've made that same signal on the little PIC, I'll develop upon it, I'll improve upon it, I'll make it do lots of other things. And that's the sort of 4 phase that we're about to go through. So here's what I'm going to do it on. This little development board is fascinating. I've had this for about 4 or 5 years now. It contains a PIC 16F18855, which is one of the bigger PICs. It's got all sorts of groovy stuff on it, which you will probably be seeing. We've got 1 or 2 other things planned to do with JAL and to do with servos and to do with things that will probably involve me using this board or the chip that's on it. The chip again has 4 LEDs, a push button, and a pot driving an ADC. It's also got a microbus socket. Microbus are a company out of Belgrade, capital of Serbia, and they make these this microbus interface. And the microbus interface is essentially an SPI interface down one side and an I2C interface down the other, plus 2 or 3 control pins and power pins and so on. And you can plug practically anything into it. The beauty of that is that there's now over 200 different little boards you can plug into that microbus socket. So practically anything, switch-wise, rotary encoder, potentiometer, relay, MOSFET, anything you could think of that you'd want to develop for, you can probably get a microbus plug-in card to do it for not a lot of money. They're very, very cheap. The lower half of that microchip development board, below the white line, is the programmer. This is fascinating. This is a 16F 25K50, I think, an 18F 25K50 chip. And what happens with that is you plug that in via the USB socket at the bottom, plug that into your PC, and a new drive appears, F drive or G drive or whatever. And this new drive is 128K in size. That's all the size it is. But if you drop, drag and drop a hex file onto that drive on your computer, it gets transferred via USB to that PIC, and that PIC then programs the 16F1855, and all the programming is done automatically. It doesn't do debugging, it doesn't do anything else. It's simply, you write the program, drag the program into the F drive, and boom, it's on the PIC and the PIC starts working. And if your PIC doesn't work, you change the program, drag it onto the F drive again, and away we go. It's very, very simple. And as I say, it's not too bad, £16 for both the development board and the programming solution. So before we can go any further, I've got to talk about ASCII. We're going to send information in serial format to a PC. The standard way of sending that serial information is ASCII, the American Standard Code for Information Interchange. Now, you've probably all met the ASCII table before, but I'll get to it. At the top of JAL Edit, there's a little group of 4 buttons. The first of these 4 is the calculator, and it's nothing to do with JAL Edit. JAL Edit simply opens the Windows calculator. So on Windows 7, it opens the Windows 7 calculator, and Windows 10, it opens the Windows 10 calculator. I tend not to use it. There's a really nice programming calculator in there, but for reasons to do with me being very, very old, I only ever use HP calculators that don't have an equals button on them, and there's not a version of that for Windows and the Windows system yet. I've got my own emulators, but there's not one of those for me, so I don't use the Windows calculator. Next to that, moving from right to left, there's a little thing that looks like a plug, and that's the Windows terminal. We're going to make serial data come out the serial terminal. Well, that's the serial terminal we're going to make it come out of. The 1 second from the left is the JAL string tool, and what that does is lets you take a string and it converts it into JAL to send that string. And there's 2 or 3 versions there, one for serial like we're doing, and another one for sending it to an LCD display. We'll not be covering it here. It's something else that we might cover some other time. Similarly, the ASCII, the last of these is the ASCII table, and I will mention it briefly here, but you could spend a whole Sunday talking about the ASCII table. There's a whole load of learning can be done about this very, very simple wee table. This is the thing whereby you send a binary number, a hexadecimal number, a decimal number, whatever, and it gets converted to a letter of the alphabet. This is where in your computers, numbers become letters and letters become numbers. Now, if you look at the top left of the ASCII chart there, just there, there's a 16 and a $F. If you press the 6, these are radio buttons. If you press one, the other one pops out. If you press the other, it pops out. 16 means that all the numbers there, every box has got a number on it. And if you press the 16, then all those numbers will be decimal numbers. So you go 98, 99, 100, 101, and so on. If you press $F, then you get them in hexadecimal numbers. And I tend to think in hexadecimal numbers. And I think a lot about the character U on the ASCII table, because the character U on the ASCII table, as you can see, is 55 hex. So what, they all cried? Well, 55 hex is 0101, that's 5. 0101, that's 5. So in binary, it's 01010101. So if I push that out through my serial port, then at every bit, the output for the serial port will change. I'll expect to see zeros and then ones all the way through, and I can use that when I'm going to school on my ASCII. Yeah. So let's simply generate very quickly using this big PIC serial sender. So in MP Lab X, I start a new standalone project. It's going to use this PIC 16F 1855, and I'm going to use no tool at all. And that's the only compiler I've got installed, XC8. And I'm going to call it 16F 18855 UART. UART stands for Universal Asynchronous Receiver Transmitter. That's what grey-haired old beardies like me call serial send and receive. in computer talk. And I press the button and I've got a project complete. Now, I'm not even going to start writing the project. I'm going to use the Microchip code configurator tool, which is, I have to say, magic. If you look up at the top in the center of the display there, there's two little shields. One says DV and the other one says MCC. There's the MCC one. It stands for Marylebone Cricket Club, but it also stands for Microchip Code Configurator. If I press that, I get this. Over to the right, the chip, all the pins and what's connected and what I've got access to and what I've not got access to. In the center, the current setup. I'm not going to alter it. I'm not going to change the frequency. I'm not going to talk about brownout timers or watchdog time or nothing. I'm not doing nothing there. Over to the left are the resources that are available to me. So I take my mouse over to the left and I make the resources available to me just a wee shade bigger by stretching it. And halfway down the resources available to me now, I see the EUSART, Extended Universal Synchronous and Asynchronous Receiver Transmitter, which is Microchip's way of saying we've got a UART as well, but it's bigger and sexier than a standard UART. So I simply click on it, open the little arrow next to it and add one of those to my project. I've now added it to the project. If you look, because it's added, there's a little red cross there. If I press that red cross, that'll unadd it to my project. That'll take it away. When it appeared there, I pressed a red plus and the red plus made it appear. Because I've added it, I've now got the USART tab and it's popped up here. And again, I haven't done anything. I haven't typed anything. So far, I've only used the mouse. The USART details are in front of me. It's asynchronous. I want it enabled. I want it able to transmit. I want it able to receive. And I want 9600 baud none 81 because that's the standard that everything is. And because that's the standard that everything is, that's the standard that Microchip make it when it opens up. So for that reason, I don't need to touch anything. I just need to press the generate button and it generates it. And I've now generated all these files. Down here, I've got main.c, which is the program that I'm actually going to write. And then I've got files that were set up by MCC. One of them is usart.c. I'm going to have a look in there, I think. In usart.c, I can see this function here. There's how to write to the usart. Well, that couldn't be easier. I type usart underline write and then give it a piece of 8 bits of data and it'll do it. Okay, so that's all I need to know. Now, if I go to my main C program, I can write the code. And there it's there. USART write 0x55. Now, 0x55 we've already established is 0101, sorry, 01010101 in binary or capital U in ASCII. And then wait 500 milliseconds, half a second. So it should spit out a U, and then it should wait for half a second, and it should spit out a U, and it should continue doing that indefinitely. And here it is on the scope, spitting out its U's. And this is where I start and go to school on what's going on here. I'll maybe move my head just a wee bit there so you can see better what's going on. You can see the trace at the top, and where it says RC6, that's the pin that I made, or not that I made it, that in fact, if I go back just a little bit, you can see that the transmit is coming out on pin 17 TX is on pin 17 of the chip. And so that's where I'm going to put RC6, pin 17 is where I expect to see this stuff coming out. And there's RC6, I put a label on it. There's the signal. The voltage doesn't really matter. As long as it's more than about 2.5 volts or something, it'll be detected. This oscilloscope has got a decoder. Over to the right, you can see the decoder, and I'm using that to decode the character. And if you look at the bottom, there's a capital U. So the oscilloscope has worked out that that's a capital U. So let's go to school. First of all, to set the trigger on the one there means I'm looking at channel 1. I've only got one channel switched on in the scope. Channel 1 is the channel I'm looking at, and I'm triggering it when it goes from high to low. That little symbol with the arrow says that this triggers when the scope signal goes from being a high signal to a low signal. And if you look over here to the left, you can see that there's the trigger point, and the trigger point is where it leaves being high and goes to low. Now that's important. That means that my signal, when it's not doing anything else, is high. It's a 1, and it goes low when it starts outputting the ASCII. But most of the time that it's not doing anything, it's high. And there's the zeros and the ones and the zeros all the way across. And I told it I wanted 9600, none 81, which is no start bit, 8 data bits, 1 stop bit, N81, none 81. No start bit, so it just starts with the raw ASCII. The 8 bits are the ASCII, and then the stop bit. However, there's a slight problem here. The stop bit is a 0 as well. So that is 5 zeros with 4 ones in between. So it could be that that's the answer, that I've got 0, 1, 0, 1, 0, 1, that the most significant bit comes first and the least significant bit comes last. But it could equally well be that the first 0 is the stop bit and the last 0 is the most significant bit. That could be the right way around. I don't know. I haven't established that. However, I have got the timing sorted out, which is really all I was trying to do initially. The oscilloscope's set to 100 microseconds. 10 shakes per division. And if we look at the division, that looks like the bit length is about 100 microseconds. Also, the oscilloscope has a cursor right in the middle, and it's currently at 404 microseconds. The cursor I'm talking about is that little arrow there, and that it reckons is 404. So that could be it could be that each of those bits is 100, 101 microseconds. I'll use that as a jumping off point for my first guess. And as I said previously, there's a decoder here. It's decoding RS232, and it's seeing at 9600 baud a U. So we've learned quite a bit from that one look at the oscilloscope. And we plug it in to our little FTDI chip, the FTDI module, and sure as a cat's a hairy beast, there we are, U space, U, U, U. Every half second I get a U appears. So it's doing exactly what I expect it to be doing. So that should about work. This is my first attempt. The top half of that program, down to line 16, is bog standard for anybody that's writing anything with this little chip. The little chip's only got 8 pins, so you can't really have an external oscillator if you're still going to have any pins left. So you need to use the 4 megahertz internal oscillator, and there's no brownout and all that good stuff. I declared my pins, I declared the direction. one for a lead and one for something that I'm calling serial. I set serial to 1 because I expect it to rest in the 1 position. And then if I output 0, 1, 0, 1, 0, 1, 0, 1, and in between I leave a delay of 100 microseconds, it shouldn't be far off. So let's try that and see what we get. Now this has got the RC6 label on it. This is the one that came out of the RS232 generator. This is the one that came out of the PIC. And it's not decoding to a U, it's decoding to a dot. And if I go back again, you can see, looking at the cursor, the 404 microseconds on the good one takes 4 bit lengths exactly. On this one, I get 4.5 bit lengths for my 404 microseconds. So this is just a little bit quick, a little bit faster. I'm not going to try anything else until I sort this timing out. Now, the scope has got a clever trick on it, whereby I can adjust the baud rate just above my head there, right? Just up here, see, it says baud 9600. I can tweak that. There's the gap, and I can tweak the baud rate there, like that. I'm going to take it up to 10,560. The scope says, yeah, that's a U, that's a capital U, you're good, that's golden. And the 10,560, I took that up to that number because that's 10% of 9600. If I add 9600 and multiply it by 110%, I get 10,560, and that works. So at that point, I can go back here and up my delays by 10%. The 100 microsecond delay becomes a 110 microsecond delay. And lo and behold, it works. Now at 9600 baud, it decodes a capital U. Now we've still got some stuff to do, but we're making progress. Remember I said, it's not about me, it's about you. Well, we're going back to you again. We're now using this lowercase u. Capital U in ASCII is 55 hex. The lowercase is 75 hex. Now the beauty of that is that 7 is 0111. So now if I put 75 hex or small u into my ASCII generator, I should see the 7 as being a block of 3 bits together. And that'll tell me what way around it goes. And there it is. And the block of 3 is over to the right. So it reads from right to left. The most significant bit, the 0, is the last bit coming out of the PIC. And then the next most significant bit, and so on. The least significant bit gets sent first. And the stop bit, the bit to tell the RS232 to stop, I don't make the standards, I don't make the rules, but that's what it is. The stop bit gets sent first. How fascinating. And again, I never try anything without testing it. I plugged it into my little FTDI port, and lo and behold, I get small U's, so it's working. So I'm now ready to write some code, and I know quite a bit. I know that it rests high. I know that it always starts with a stop bit. Don't ask me why it always starts with a stop bit. This is like the Russian cosmonaut on the International Space Station who was given a Windows PC to operate, and he wanted to shut it down, and they said, yeah, well, the first thing you've got to do is press the start button to stop it. Well, that's the way this seems to work as well. 8 bits. Least significant bit first, most significant bit last. Leave a little bit of delay. 110 microseconds seems to be good enough for what we are doing, but it's better if we can tweak that delay. First of all, if my code, if I add extra code and that extra code takes time to run, then I may have to tweak the delays, make them shorter to compensate. Next, chips, ASCII. Now, if you haven't heard of ASCII, I'll explain it later on in a wee minute or two. But basically, there's an internal oscillator. We're not using the crystal oscillator in the chip, so it's using a semiconductor oscillator. That semiconductor oscillator is sensitive to temperature, local capacitance effects, even power supply voltage. And for that reason, you sometimes have to calibrate it. And the calibrations can be radically different. So for that reason, you need to be able to tweak your delays. Also, the applications, what Charlie's doing might not be exactly 9600 baud, or 9600 baud might be too fast or too slow for his job. So we might have to change it that way. And the receiver, where it's sending it to, certain PCs might not like certain 9600s. They might be sloppy or might be tight or might not like jitter. So again, because the PC might be sniffy about it, better to make it tweakable. Which leads me on to a couple of wee sidebars that we've got to talk about. Delays. There are two delays available in JAL. His head is in the front of the text. There we go. There's the microsecond delay, which is underline USEC, underline delay, and then a number. And this is actually understood by the JAL compiler. It's baked right into JAL. It actually gets compiled. You don't need a library. You don't need anything. What you do need is a constant. Now, there's two types of constant. There's implicit constants and explicit constants. An implicit constant, like 100, is a constant that's a constant because it's a constant. 100 doesn't equal 99 and it doesn't equal 102. It equals 100. It's implicitly equal to 100. Or I can have an explicit constant, like I declare t equals 100. And now t is a constant because I've declared it explicitly to be a constant. But if I'm going to use the microsecond delay, I have to use a constant, one of those two types of constant. If I try to use a variable, not only will it not work, it won't even compile. Because it's a compiler function, you'll get a compiler error. If you try to put microsecond delay with some variable that you've declared in there in the delay, it won't work. You will get a compiler error. The other type of delay is the delay underscore 1 microsecond or delay underscore 6 microseconds or whatever. And that isn't built into JAL. That's an external library that somebody wrote. We'll talk about the libraries in a wee while. And inside that external library, it simply uses the other one. If you tell it to delay 1 microsecond 100 times, it'll do 100 of the 1 microsecond delays. It just uses the same baked-in thing inside the library. But the difference is that this time it will take a variable. So I can set that variable. So I can make that my pot sets the delay because it's variable when it's running. But I can, I find rather that when I'm using this, the delays that you get might not just be as reliable as they are if you do the baked-in constant delay. So it's a thing to think about in all your JAL, that you might want to use microsecond delay or you might want to use delay microsecond. And there's masks, right? You should always wear your mask. A mask is when we use 1 byte to mask off another. In this case, the mask is the top number with just the 1 in it, and the other number, the 11001011, we're calling the target. And we take the two numbers and we AND them together. And because of the AND function, if they're both 1, then there's a 1 in the result. And any other result, if one or the other is a 1, or if they're both 0, you get a 0 in the result. So that's the mask having an effect in passing a 1. There's the mask. If I masked it to that bit, I would get a 0. And the reason that we do that is if I'm making a JAL decision, like for example in an if statement, then 0, 0, 0, 0, 0, 0, 8 zeros is considered to be equal to false. And anything else, a 1 anywhere, is considered to be true. So if you look at that, that says, is there a 1 in the first bit of the target? Yes, true. Is there a 1 in the second bit? Yes, true. Is there a 1 in the third bit? No, there isn't. False. And so by clicking a 1 along there, I can find out whether or not that bit contains a 1 or a 0. And that's what I'm doing here. If B and 1 equals 0, then it becomes a 0. If B and 2 equals a 0, then it becomes a 0. Otherwise, it becomes a 1. And this is the procedure. It comes in, started high, and then it immediately goes low for the stop bit, for whatever my delay is. My delay is a constant, so that I can rely on the constancy of it. And then I use the mask 8 times to decide for each of the bits if it's a 1 or a 0. If it's a 0, I make it a 0. I make the output a 0. And if it's a 1, I make the output a 1. Once I've finished, I make the output back to being a 1 again to leave it as a 1. And then I wait for about 3 bits length and I'm finished. To call it, all I need to do is, if I just go back there, the procedure that I wrote was called serial send, and it expected to see a byte. So to call it, I simply call serial send with a character, like T or an E. ASCII 13 is carriage return, so that should make something appear on a new line. There it is on the oscilloscope. The oscilloscope decodes it. If you look at the bottom line, it says TEST space carriage return, which is exactly what I was hoping it would do. And there it is coming out the mini terminal. So it's working. I've now got a working version. And I'm now at the stage where I'm thinking about how do I improve it and make it better or whatever. This is called an unrolled procedure because what it's doing is unrolled. You can see that it's the same thing 8 times. Now I can roll that up to a rolled up procedure where I simply say, do this 8 times. And there's the rolled up version. Giving it the same name, everything else is the same, except it's while n is less than 8, I move x along n characters. And then I do the same masking trick. And then I do the same constant delay, and n moves up to the next one. So it's n equals 1, n equals 2, and so on. So that's the same code, but it's been rolled up. And the reason that I roll it up is that that version there has got all those implicit constants in it, all those 1s and 2s and 8s and 16s and 0s, and all of those take up space. And there's how much space. The unrolled version takes up nearly twice as much space as the rolled up version. Now, the rolled up version, when I made it work, was a bit less stable because it turns out that the shifting of the characters in can make the delays just a little bit longer, makes the bit delay just a wee bit longer. So I had to tweak the DLY constant to get that to work properly. But I did, and it worked. The code space, as I say, is 247 for unrolled or 117 for rolled up. But that's the worst possible case, because my little program that I'm using to test it has got its own COM block. When you compile anything, the compiler has to put its own wee bit of code at the start that says whether there's interrupts, where the interrupt block is, what variables it's using, how much stack it's using, how much storage it's using, where it's putting the stack, various settings that the machine needs to know. Now, this little program that I ran had one of those because it's my program. But if I am just going to plug this routine into another program, then that other program will have its own COM block. And so my COM block won't get added, it'll use Charlie's COM block. So for that reason, that 247 and 117 will be the most that it will add to the program. In reality, I would expect it to maybe add 200 bytes unrolled, maybe 70, 80 bytes for the rolled up version. So it's not just as bad as it looks there. And even there, it doesn't look that bad. So, some points to note, well, a couple of wee things to do before I finish. If you want to go slower, I started at 9600 baud because 9600 baud is the standard value for this good stuff. If you want to go slower, then you can see that as the baud rate halves, you double the delay. It's as straightforward as that. And you can twiddle these, you can compensate them. And you should add, there's a thing in microcontroller design called delays that are blocking or non-blocking. A blocking delay is when the delay is happening, you can't do anything else, right? And a non-blocking delay is when you can start the delay and then go and do something else while the delay is running out. Now, the PIC compiler uses timer 0 to make its delays non-blocking, but it is good practice to treat these delays as being blocking delays, because if you do practically anything else, it will cause the ASCII to become corrupted. Take that from somebody who has corrupted many an ASCII. And so we're just about done. I take my little routine and I package it into its own little library, which I am going to call 675debug.jal. I then copy 675debug.jal into the libraries folder on my jallib workplace. I'm then going to write a very, very simple program that tests it, which is basically the same program that I've just used. And I'm going to run it again and check if it still works. There's the debug.jal. There's my serial send at the bottom. I've left these other ones incomplete because if I filled them in, people would just use them. And if you use them, you're going to waste a lot more bytes than you would gain by simply using the simple one. You can write those if you want, you can flesh those out if you want, but really, you don't have room. Inside a 675, you don't have room for silliness like that. And there's the program to call it. It's simply, that's the usual standard. Down here, it includes 675 debug, and then it calls it. Right. And a couple of little caveats before I finish. Now, this is not a JAL course. I say that there's a JAL SIG. Fraser and the guys worked really hard to help people programming in JAL, and that's not what we're here for. If you go to the JAL SIG, they will make you most welcome and they will show you all sorts of groovy stuff. But there's one or two wee things here that if you're an irregular JAL program are liable to bite you, and so I'll just go through them. I've already mentioned the ASCII, and I've spelt it wrongly in that slide. It should be OSCCAL, which is the oscillator calibration. The chip has got this semiconductor oscillator on it, and the semiconductor oscillator isn't particularly accurate, but you can calibrate out how inaccurate it is. And in order to do that, they used a very sneaky little trick. The chip has got 1,024 spaces in it, data spaces, or spaces for program words. They're numbered 0 to 1023. Now, if you call a subroutine, then that subroutine has to have a return. So if I called the subroutine at position 1023, then there's no way that that subroutine is ever going to call back. So what they did was they put their own wee private secret subroutine at 1023, which is OX3FF. 3FF hex is 1023 in decimal. So what I do is I go to bank 1 of memory and I call 3FF, and it will return. How it will return, I don't know. It's down to the internal workings of the chip, but it will return. And when it returns, the working register of the chip will have a value, some number between 0 and 255. And that number, if you take that number, it won't mean anything. But what it will mean is that the oscillator has been calibrated. You don't have to do anything with the number. You can look at it if you want. Doesn't mean anything. But the very fact that you called that routine calibrated the chip, and your chip's now as close to 4 megahertz as it's going to get on a semiconductor oscillator. I've put that as a procedure, and you can copy that procedure from there and use it if you want. In reality, it's there as a procedure because it lives in my great big file of handy procedures. I wouldn't use it as a procedure because if you call it as a procedure and then end procedures are returned from subroutine, that wastes a number of bytes. In order to call a procedure, you have to call a subroutine and you have to call the address of the subroutine. And once it's finished running the subroutine, it has to then do a return from subroutine. And those are wasted bytes. And in this little PIC chip, you've only got 1,023 bytes, and every one of them's a prisoner. So what you do is you copy the bit from assembler to end assembler, copy and paste that in at the start of your JAL program, and that'll calibrate the oscillator without wasting 4 bytes on a procedure call and a return. Microsecond delays versus delays microseconds, I talked about a few moments ago when we were discussing it, so I'm going to leave that alone. The blinking light. My program has got as you may have noticed, I declared a LED, and every time I go round about the main loop, that's the main loop on my JAL program is the forever loop. And it starts with forever loop and it finishes with end loop. And every time I go into that loop, I tell it that LED 1 becomes equal to whatever LED 1 isn't. If LED 1's a 1, make it a 0. If LED 1's a 0, make it a 1. And what that means is that every time it goes round the loop, my wee LED flashes. So when I plug the board in, if it's working, the wee LED goes and blinks. If, however, the program gets stuck somewhere in here in the body of the program, it gets jammed, it finds a number it can't reach, or it gets to a test that never happens, or there's 100 ways to stall a program. But if the program stops, then the LED stops as well, because it stops going round about the main loop. And as a result, all I need to do is plug the board in, and just by looking at it, I can say, yeah, it's running. It's going round about the main loop, because the main loop LED is flashing. It's a wee con, it's a wee trick, a little hack, but it will save your life one day. Inspecting include files. There's something that I encourage people to do all the time. There's an include delay. I said earlier that the delay JAL library is written purely in JAL. Now I can prove that. What I do is I put my cursor on the word delay, and then I right mouse. And when I right mouse, there's an option halfway down, open the file at cursor. So I go down there and I click open file at cursor, and lo and behold, delay.jal opens. And here we are inside the delay routine, and we can see how the delay routine works. And by the time you're up using millisecond delays, it's actually compensating for the length of this code. Can you see somebody has actually spent a day tuning this and making sure it's right? No, which is lovely. But that also means that if you use the delay 1 millisecond, you add all this code to your application, which is fine most of the time, but not in the 675, because the 675 doesn't have space to play with. It's quite snug for routines. But feel free to get into any of your includes, which brings me on to this. If you actually go to the lib directory, there's a JAL file for every chip, but there's also hundreds of other JALs for LCDs. There's 6 different CAN libraries for different aspects of using the CAN bus. There's SPI, there's timers, there's things for LCDs. There's things there I've just noticed for a dog. I've got no idea what dog is. Digital overlay, I've no idea. There's all sorts of interesting things there. And if you're doing anything in JAL, there's a good chance that you're using something. You don't need to reinvent the wheel. All these are already written. They come as part of the JAL lib. They're in the lib directory on your JAL workplace. Go and have a sniff, have a wee nosy. Lastly and finally, when I'm including includes, here's my final little program, my little debugger. At the top, I include the file for the chip that I'm running, the 12F675. Down at the bottom, there's an include for the debug, which is the one I just wrote. Now, if this was C, you put all your includes together. They're a preprocessor thing, and it would be hash include 12F675, hash include 675 debug, hash include delay, hash include this, that, and the other. JAL isn't that clever. You have to think a wee bit when you're using an include in JAL. And this is where a lot of people make a mistake that's quite easy to iron out. My debug routine, which I call at line 18 there, uses LED 1, which gets mentioned. No, it doesn't. The main program uses LED 1. It uses the serial pin, which is declared at line 13. And it uses pin A1's direction, which is declared at pin 15. And it also uses that delay. And the delay is declared at line 17. Right? It uses the pin, which I'm calling serial, which is declared at line 13. It uses the direction for that pin, which I'm calling serial, which is declared at line 15. And it uses the delay constant, which is declared on line 17. So I can't include, when I include an include file, all that the compiler does is it takes the contents of that file and it jams them in there where that line is. So for that reason, I can't use any of these things, serial or the delay or any of that stuff, until I've actually declared it. So I can't include it until I've declared it. And so that include has to be after the declaration for the serial and after the declaration for pin A1's direction and after the declaration for that delay. So line 18 is the first line that I could put that include on. If I put that include any further up the program, it'll crash, because when the compiler gets to include 675 debug, it'll say, I've never heard of serial, or I've never heard of DLY. And so it'll look like I've got a compiler error because I haven't included something that I have included, and it's to do with the order that the includes are set up in. It's an easy thing to get caught in. Try not to. And at that, I think I'm done. The software that we've used today has been this. There's nothing there that's exciting or new or cutting edge. They're all pretty regular. I used a PIC kit 4, but you can use a PIC kit 2 or a PIC kit 3 or a PIC kit snap or an ICD or whatever you've got to program your 675. The scope that I'm using is a cheap Rigol DS1000 series. And there's the number of that little microchip development board in case you're interested in that. Everything that I've just shown you is in the file called 675 serial, which I'm now putting up on the chat. It includes this PowerPoint presentation. It includes all the source code for everything, all the JAL files and all the hex files. I'll also include all the assembler and all the code and all the output, the whole lot. It'll come to about 8 megabytes. My email's at the bottom there if you want to contact me about this or about anything else, but you know that already. And if there's any questions or comments, I'll take them now.